Okay, this is our video number 2. This is section 9.6 on trig sub. You've probably spent some time on trigonometric integrals. This has got the same idea of trig, but it's really an algebra technique, not a trig technique. So many students find this confusing. You might want to watch the video a couple of times before you try the exercises. Let's look at a problem. We're trying to integrate. This is example 1, page 457 or 457. 457. Example 1, the integral of dx divided by square root of x squared minus 9, or if you want, the integral of x squared minus 9 to the negative 1/2 power, right, times dx. And so you might think this is a power rule, u to the n du, but pretty quickly you can see that doesn't work. If this is our u, right, and the minus 1/2 is the n, the du would have to be 2x dx. We don't have a 2x dx. We had no problem with the 2, but we can't introduce a variable into the integrand. So this is not a power rule the way it stands. And in fact, if you go through all the other techniques you try, even integration by parts, this doesn't seem to crack at all. And yet there's a simple way of doing that if we know that, let's see, do I want to do this one first? I probably don't want to. In fact, I'm going to start this whole video over. So let me just stop right here, and I'll pick this up in just a second. Okay, back again. Sorry about the hang up there. I don't have any real problem with this, but the first example I wanted to give you was one that had not the square root of x squared minus 9, but the square root of 9 minus x squared. And you'll see that they sort of have a similar flavor to them, but most students will find this one a little bit easier. And let me just go ahead and throw an x squared in here as well. So this is not example 1 in the book. In fact, it looks a little bit more complicated, but in point of fact, I think you'll like this one a little bit easier. Okay, so what am I supposed to do with this? And why is this called trig substitution? Well, what I'm going to do is I'm going to note when I see this particular setup, when I have a square root of a squared minus something squared, whenever I see that, I'm going to use this fact. I want to write let u equal a sine theta. So for this problem, where I have the square root of 9 minus x squared, I'm going to say let x, that's going to be my u, equal 3 sine theta. Now, when students first see this, they go, whoa, crazy. Why are you putting trig and why are you putting thetas in? This integral has an x, it has a dx, it has a square root. Granted, that's not really pretty. There's a 9 and an x squared. Why are you turning this into trig? And the answer is because it works. It's sort of like this is the way you do these problems. Okay, now coming back to the integral in just a second, let's sort of look at this box for a second. You would agree that x over 3 is the sine of theta. And in fact, let me draw a little right triangle. In fact, all of these trig substitution integrals, we're going to be drawing this right triangle. So here's an angle theta, and it says the sine of theta is x over 3. Sine is opposite over hypotenuse. Remember, sine is opposite over hypotenuse. What does that make of this longer leg, or this second leg down here? Let's see, Pythagorean theorem. Let's call that a for a second. A squared plus x squared is 9. So a squared is 9 minus x squared. So a is the square root of 9 minus x squared. That's interesting. the square root of 9 minus x squared. That did appear in my integral. And in fact, every time you have an integral that has a constant squared minus some function squared, square root, you're going to use this substitution. And you will always draw this picture, right? The a is going to be the whatever the constant is. In this case, it's 3. And the missing side will always be this a squared minus u squared. It will be sitting in the triangle. You say, okay, I sort of buy that. Where is this going to help? Okay, let's chase this one substitution down and see where it leads. If x is 3 sine theta, we know x squared is 9 sine squared theta. We know that. And the reason I'm going to need that is because in this particular problem, there is an x squared. And what else do we need? We need to know what dx is. Let's see. So if x is 3 sine theta, we know dx is going to be 3 cosine theta d theta. And I need to know that because that's also in the original problem. Okay, and lastly, we need to figure out what that radical is. Well, let's look at the picture again. Would you agree that the cosine of theta, looking at this picture, is the adjacent side divided by the hypotenuse? I would hope that you would say that. So that the radical, 9 minus x squared, is going to be 3 cosine of theta. Let that sink in just for a second. Okay, now, we've done a whole bunch of stuff, but we haven't really changed the problem. We are now going to change the problem around, and I'm going to sort of pin down all the things that we've said. We know that x squared was 9 sine squared. We know that dx was 3 cosine theta d theta. And the other thing we did was the square root of 9 minus x squared, we said was 3 cosine of theta. Okay, so all of that is information that we've sort of pulled out of this picture, right? And again, this picture is all coming from the fact that the sine of theta was x over 3. Okay, so let's take all of those things and we'll do a massive substitution. This is called trig substitution. So we still have an integral. 1 still stays 1. Okay, x squared is now 9 sine squared theta. The radical is 3 cosine of theta. And the dx is 3 cosine of theta d theta. Right, so that's all the substitutions. And then let's see where this chases down. I'm going to pull the 1/9 out. The 3's cancel, the cosine stay. It looks like we have 1 over sine squared, or if you want, 1/9 the integral of cosecant squared. And that should be one of our basic formulas that we remember way back from an earlier chapter. Just to refresh your memory, let's see. The derivative of tangent is secant squared, right? The derivative of cotangent is negative cosecant squared, which meant that the integral of cosecant squared is negative cotangent. So you're supposed to know that from way long ago. So we have the integral of cosecant. So we get negative 1/9 cotangent of theta. Now, at that stage, you think you're done. But in point of fact, you're not. Notice that the original problem, there were no thetas here. There were simply x's. So we did this. This is the substitution to turn everything into thetas. We've integrated using thetas. So we've got that answer. But now we have to turn everything back into x's. You say, how am I supposed to do that? And the answer is you go look at your picture again. Here was the picture. And now the question is, what is the cotangent of theta? So let's remember our trig again. The tangent of theta is opposite over adjacent. And so the cotangent would be adjacent over opposite. So we have minus the square root of 9 minus x squared over 9, right? That 9's still there, x plus a constant. Okay, so this is the answer to the original problem. The original integral evaluates to that. Okay, let's do one more using this particular type of problem, and I'll pull one out of the book now. Let's go to the exercises. We'll do, I want one that has a constant squared minus a function squared, and see if we can work that out. Okay, so let's go to problem number 19. So this is in the problem set, problem number 19. Again, I've given you the solutions to these in the back of the book, so you can go back there and play with these on your own. This one has a dx, and it has a square root of 9. Wow, they like that 9 again. But now instead of x squared, it's x minus 5 squared. And the task is see if we can integrate this. Okay, so whenever you have the square root of a squared minus u squared, I want you to write u is a sine theta. That's the task. Right? A sine theta. Okay, so in this problem, a is 3, and the u is x minus 5. So this is what we're going to write. And now I need to draw a triangle with that. So here's my little triangle again. There's my angle theta. Notice that the sine of theta is going to be x minus 5 over 3. So 3 is the hypotenuse, and x minus 5 is over here. And then using Pythagoras, this will again be the square root of 9 minus x minus 5 squared. Okay, so we have that integrand appearing in there. And then just so that we're convinced that this is going to help us, the cosine of theta is going to be adjacent over hypotenuse. So the radical is going to be 3, right? Radical 9 minus x minus 5 squared is in fact going to be 3 cosine of theta. Okay. The only other loose end we need is what is dx? Well, let's go to here. We know that x minus 5 is 3 sine theta. So x is 5 plus 3 sine theta. So dx is the derivative of this. The 5 goes away. 3 cosine theta d theta. Okay. So now let's go ahead and make all of these substitutions. So using the substitutions that we've got, this integral turns into another integral. Dx is going to be 3 cosine theta d theta. The radical we said was 3 cosine theta, 3 cosine theta. So obviously all of this cancels out, and we're simply integrating d theta, which should be easy enough, is theta. So you think you're done? Well, of course you're not done. You have to turn it back into x's. And so we look at our picture and we go, well, here's our picture. What is theta? Well, theta is an angle. And I suppose we can do this a number of different ways. We can do arc sine or arc tan or even arc cosine. But since we're dealing with sines here, let's go ahead and use arc sine. Theta from the picture is an arc that has a sine of x minus 5 over 3. So our integral is, this is the original integral that we had to deal with, dx over the square root of 9 minus x minus 5 squared works out to be the sine inverse of x minus 5 over 3 plus a constant. Okay, Now again, that may ring a bell because I think we actually had earlier in the year, I made you sort of memorize the integral of 1 over 1 plus a squared, or sorry, a squared 1 plus x squared dx was the tan inverse of x, and we had 1 over a squared plus x squared was 1 over a tangent of x over a. So you may remember those. And then along with those, we had this one, 1 over the square root of 1 minus x squared dx was the sine inverse of x plus a constant. And its companion piece was this square root of a squared minus x squared dx is the sine inverse of x over a plus a constant. So that may sort of harken back to this particular problem, right? Instead of x, we have this ugly, there it is, and we still have the a on the bottom. Okay, so that's one out of the problem set. And you can play with any of those using that particular trig substitution. Let's go back and pick up the one that had the x squared minus 9. So for x squared minus 9, we're going to have a slightly different substitution, and I might as well go ahead and write all three of these down. Whenever you have the square root of a squared minus u squared, that was the one that I did first, I want you to write u is a sine theta, and then draw the triangle, and the triangle will always look like this. This is your theta, this is your u, this is your a, and this will be the square root of a squared minus u squared. So that's using that particular one. The second substitution that comes into play is if you have the square root of u squared minus a squared, then I want you to use this particular substitution. U is a secant of theta, and again, you can sort of think how this goes. The secant of theta is going to be u over a, or if you want, the cosine of theta is going to be a over u, right? Secant is the reciprocal of cosine, and that picture will look like this. Okay, so once again, put your little angle down here. Now we're going to have the a and the u, and this now is the square root of u squared minus a squared. Right? The cosine is adjacent over hypotenuse, so that's the a and the u, and then use Pythagoras to get that. That's the second one. And the third one is going to involve, again, a square root, but this time we're going to have an a squared and a u squared added together. So a squared plus u squared, or if you want, it doesn't really matter. It could be u squared plus a squared, right? Addition is commutative. For those guys, I want you to use this u is a tangent of theta. And again, we can draw our little picture if you like. Okay, so same triangle. There's your theta. Notice that the tangent of theta is going to be u over a. So tangent is opposite over adjacent, and then this will be the square root of u squared plus a squared. So when you run into integrals that have radicals, and it has something squared and something squared, if they're added together, you use u equals tangent, a tangent theta. If they're subtracted, you're going to use secants or sines. The first one that the author had, right, his example one, was this second type. So let's go back and look at example one more time and see if it now makes sense. So we have this integral of dx over the square root of x squared minus 9. You go, oh, there's my u squared minus a squared. I want to say for this problem, x is going to be 3 times the secant of theta, or if you want, the secant of theta is x over 3, or the cosine of theta is 3 over x. And here's my picture. There's the theta. The cosine is adjacent over hypotenuse, and this now is going to be the radical, right? So x squared minus 9. Okay, let's see. What do we need? we need to know what the radical is. So looking at the picture, we need to replace this radical with something. Okay, so in this picture, I note that the cosine of, not the cosine, I want the, let's see, the cosine would be 3 over x. That's not what I want. I want the sine of theta. I don't want that either. I want the tangent of theta. Let's do that, because I really want to avoid the x if I can help it. So the tangent of theta is radical x squared minus 9 over 3. So the radical itself is 3 tangent of theta. That takes care of the radical. How about the dx? Because we've got to replace all of these guys. We now know what that is. Now the question is, what is the dx? So to do that, you need to go to what x is. If x is 3 secant theta, then dx is going to be 3. The derivative of secant is secant tangent, right? Remember your derivative rules. Okay, so that's going to take care of the top. And now we'll do both of those substitutions, and then we should have our new integral that we should be able to work. So dx is 3 secant theta tangent theta, and the radical is going to be 3 times the tangent of theta. So the 3's cancel, the tangent's theta. I need a d theta. Sorry, back here. Dx d theta is all of that. Take the derivative of x with respect to theta. You get 3 secant theta tangent theta. So dx by itself is 3 secant theta tangent theta d theta. Better put that back in here, d theta. So I still have that left. Okay, so finally, my integral reduces down to the integral of secant theta d theta. And, you know, do you remember how to do that? Is there a secret to doing that? There was. We looked at that sort of as a, you know, a trick more than anything else. If you remember, you multiply by 1. I don't really expect you to remember this, but some of you probably do. You multiply by the secant of theta plus the tangent of theta. It's like a magic trick, right? You go, well, why in the world would you do that? Well, because like all good magic tricks, it works. On the bottom, we have the tangent of theta plus the secant of theta. And on top, we have secant squared of theta plus the secant of theta, tangent of theta. And we have our d theta. And lo and behold, this turns into 1 over ugly, tangent theta plus secant theta. That's certainly an ugly thing. And then we have the derivative of that. Derivative of tangent is secant squared. And the derivative of secant is secant tan. Secant theta tan theta d theta. So this actually did work out to be a log. And you might remember that. You might not. I don't think you'll be tested on this in May. Okay, so there we are. We've integrated the secant of theta. And you go, wow, finally, we got the answer. Well, we don't have the answer because remember the original problem did not have the theta in it. The original problem had the x's in it. So now we have to do the back substitution. So take away the plus c. We're still going to have to do some back substitution. Turn these all back into x's. And to do that, you need to look at the picture. So, you know, here was our picture. We had the x as the hypotenuse, 3 as a leg, and radical 9 minus x squared. So let me just sketch that back down here again. This was, we had 3 on the bottom, x here, and radical x squared minus 9. Okay, so we've got to replace all these guys. So here's our final answer. Natural log. What is the tangent of theta? Look at the picture. The tangent of theta is opposite over adjacent. So we write the square root of x squared minus 9 over 3. And what is the secant of theta? Let's see, the cosine of theta is 3 over x. So the secant of theta is x over 3 plus a constant. Now we're done. Hard problem. Come test time, these will probably be bonus questions. We've got more important things. For example, partial fraction decomposition, which we're going to do on Monday when we get back, is probably more important than trig substitution. I know that you'll see partial fraction decomposition in May. You probably will not see trig substitution in May. At any rate, you can now sort of play with these. I'm looking at the text. I would have left it here. The author actually does one other thing just to sort of see whether you're savvy. I don't know that you need to do this either. This is the natural log of the absolute value, square root of x squared plus 9 plus x over 3, right? And so this is the log of a quotient, which is a difference of logs, natural log of square root of x squared plus 9 plus x minus the natural log of absolute value of 3 plus a constant. But these are just two different constants, so call it a constant 2, and the author writes the answer this way. A lot of times when you're going to the back of the book and you look at your answer and it's not quite the same as what the author has, you go, am I right or am I wrong? You may still be right, but he's written it in a slightly different form. So this is the solution that he has on page 457. Okay. At any rate, have fun doing calculus over Thursday, Friday, Saturday, and Sunday. And I'll go ahead and stop this right here.